And basically what, this one's of the three, I think is the most confusing one. And usually it bridges barely into this, but I wanted to talk about the different kinds of precipitation problems that you could have. So yeah, we mixed two different solutions together. It said find the concentrations at equilibrium. Well, we found out that a precipitate forms, okay? So once we know that a precipitate forms, this is where we are at then. Is that we are talking about this equation. Okay? And what we are saying is that if a precipitate forms, what we just realized is that it shifts back this way because it's going to make a precipitate. So now we need to apply some material to that, okay? So what I need to do is now an ice box. I'm going to plug in the numbers that I have, and I already have them kind of right here. So from the magnesium, magnesium nitrate, I have 150 mils and 1 times 10 to the negative second molar. So I need to find out the number of moles of each of these. And I just bled in there a little bit. And then the fluoride, I have 250 mils. The whole point, I want to find how much I have of each. Okay? I have 1.5 millimoles of Mg. I have 25 millimoles of F minus. And what I figured out was I have too much of this. It needs to come back this way. And if you're, wait, how did we find that out? I compared it all. And you need to be setting this up because this is the math. This is how we're going to work this out. Okay? So it's going to shift this way. So if that's the case, so you understand, then that's going to be minus x. And this is minus 2x. Okay? Now, there's no way to get around it. This is a little bit of a confusing moment. Well, what is x? I don't get it. Because this is a solid. So I can't have anything on that side. Well then, how far do I go? I don't understand. What we're going to do is we're going to exaggerate this thing, and we're going to drive it all the way to solid, and then let it flutter back using the k. So meaning with that is I'm going to take the smallest one. I'm going to assign it 0. Again, of the three, this one is easily the most difficult of the three. The next problem, even though it sounds more difficult, there's a lot less work. So if that's the case, then x is 1.5, right? Correct? So then what is my final amount of millimoles here? It'd be 22, right? Because 1.5 times 2, right? So I'm going to have 22 millimoles right here. Okay, so I can figure this out. What do I have? 150 and 250, so that's 400 milliliters, which we've already stated once before. And I'll do the math with you a little bit here. The reason why we're going to push it back the other way, or the amount that can be pushed back the other way, it's not that we're going to run out of fluoride. We have so many more moles of fluoride, millimoles, than of magnesium. So this ran out. So right now we shoved it as far over to the side of the solid as you possibly can. So now what we're going to do, I believe we already wrote this on the board, on our notes. So you don't have to write this again if you don't want to. I just wanted to, I believe we have this from yesterday. What I need to simply do now, just like before, remember, okay, with titrations, I flood it as far over to the side and then it has to flutter back. Here, what I did is I'm forcing it as far over as I can, and then we'll just see how much kind of comes back in, because something has to dissolve. Something always has to dissolve. I can't stay at 0, okay? You cannot have a 0 in an ice box at the end. So what I can do, though, is I can plug it in now to this. So this is what I'm going to do. What's the Ksp? 6.4. Is that negative 9? Okay. I don't know x. Sorry, mg. I don't know mg. And then what would, if it was fluttering back now the other way, See if anybody can come up with this without me having to do another icebox. What has to go in there? It's going to flutter back now the other way again. So I pushed it all the way here, and now it just needs to redissociate so I don't have zeros. Plus 2x. It has to flutter back the other way. To be honest, this isn't going to matter. You're like, wait, why? I mean, it does in the idea, but like, I have so much of this, it's not going to really affect it. This is going to be minuscule. It was already minuscule, and it was still too much. It was still too much because it said that it precipitated. So just a little bit of it's going to come back. So what I need to do, like always, I can cross out things that are added or subtracted. Okay? And when it's all said and done, and don't let what we are doing yesterday and then today, just because of this, the ending of this problem, kind of shift your, let's say, equilibrium of what you understand, but your feeling of ice boxes and KSPs will still be okay. This one is just a little trickier. I got this. It's very small. 2.1. You're going to help me calculate the next one, so I'm going to do this one. Times 10 negative 6. Now, if you're like, well, okay, well, let me plug that into here. You put that in, multiply by 2, and add it to that, it's still this number. It's still the number. So, at equilibrium, that's how much is going to be there.
What is the number, 2.1?
2.1 times 10 negative 6. Sorry. Yeah, I'm kind of writing small. Apologize.
So you don't have to put the squared on the f then for the equilibrium?
No, because this is the concentration. That's a great question. The concentration and the squared, this is still how much there is. It's just the relationship within the equation. Yes, like the amount is still the amount inside. All right, so I know that's a little confusing, and the fact that we did it disjointed, just kind of, I guess, keep it in perspective. What did we do? Yesterday we figured out, will this precipitate? If you found out it wouldn't precipitate, these amounts, that would be done. You put it over 400 and that's it. Oh, how much, what's the concentrations at equilibrium, meaning either it dissolved or came out of solution. Hey, it's done. They all dissolved. We found out, oh, it doesn't all dissolve. Oh, shoot. Okay, that means I gotta push it all the way as far as I can and then see how much actually will come back into solution. So it's almost like kind of taking it out of solution as solids again, pouring it back into a liquid and stirring it up, and then whatever does dissolve will. Whatever doesn't won't.
The concentration of Mg plus.
Where did I get it?
Like how?
So then I just replugged this in. I acted like now the equation's coming back this way. So this was my F. X is, it'll be like 0 plus X. So X is my Mg. This is my KSP.
Wait, is that 0.0055 or is that
0.055. 0.055. Thank you. You're close. Okay, let's get to the last one. So then we can kind of jump into the new material here today. I think this one will click, I hope, and then maybe everything will kind of come together. Fingers crossed. Here we go. This one does not have as much work as it sounds like it's going to have. So stay with me, please. Your packet will help you a lot, though, with this as well. All right, so what I have a solution of copper and of lead. Okay? If I slowly add iodine, I'm just adding iodine in there. Which one will come out first? When iodine connects with Cu or when it comes out with Pb? And it's like, oh God, this sounds really confusing. Let's break it down and let's try to simplify it. How I simplify things, I like equations, okay? So these are the things that I'm talking about. I have CuI. Well, that could break up into this. I have PbI2. That could break up into this. The thing you don't have yet that I need to give you is the KSP of each of these solids. So let me give you that.
how are you supposed to know that? Or is that
I have to give that to you.
okay.
You're not in economics today. Nice.
You decided to have some brain cells.
Oh,
Wow, wow, whoa, whoa.
I'm wearing this blind banter, okay?
Okay, if I just ask you which one's more soluble, is it the copper or the lead or iodine? Which one's more soluble? Brody says the iodine, or they're both iodine. You tricked me. Oh, the iodine one. Yes. Dang you. The larger the number, the more it means it shifts to the right side. So if I just ask you just point blank, without knowing any other data, which one is more soluble, it is the lead. Because this dissolves more into its ions. I hope that makes sense. Okay? But it matters how much you have of it. So we could trick the number. So this is how we're going to do this. And it doesn't need to be as complicated as it seems. Let's talk about the CUI. And the answer at the ending, I hope, will make sense. So let's just talk about CUI. What I'm going to do is I'm going to put it into the KSP relationship. Remember, at the ending of this, these numbers tell us the maximum amount that can dissolve. Keep that straight and everything will be better. It's the maximum amount that can dissolve. So I have 5.3 times 10 to the negative 12 equals Cu plus I minus. So I'm going to plug these numbers in. I have 1.0 times 10 to the negative 4 times x. This comes from the copper in the problem. I don't know how much iodine. What if I just slowly add it? What I'm going to figure out is the maximum amount . What that means, that's the maximum amount that can dissolve in the relationship to the KSP. So I get an answer of this. That's an 8. 5.3, hopefully you guys on the side, sorry. I'm trying to write as big as I can. Do the PBI 2. I plug that into the KSP. I will continue to repeat this because this is what got me stuck when I was first learning this. I don't understand what KSP is. It's the maximum amount that can dissolve. So with both these equations, I plugged in the source of my Cu and my Pb. So then that's telling me the maximum amount of my iodine that can dissolve in there because of the amount of Pb and Cu already in there. So this is the maximum amount that can dissolve. The question is, if I slowly just keep adding iodine, which one will precipitate out first? Will all of a sudden there be too much of this combined relationship, this bond of Cu and I, or PbI2, and it'll precipitate out? Well, based on here, this is the maximum amount that can dissolve. This is the maximum amount that can dissolve. So if you're pouring it at the same time, which one's going to come out first? Cu or PbI? Cu, because that's the least amount, right? That's when I get to that amount, then all of a sudden CUI is going to start precipitating out. This one can hold more still before it precipitates out. And I had a good wording with this. I just wrote takes lower concentration. I hope that kind of makes sense. I thought when I did this problem just on a sheet afterwards, I'm like, you know what, I would think that that would help kind of just give me a better picture in general of what this can do for me. Okay, so maybe the question just would simply be, erase one of these, and I just say, hey, how much can dissolve? Or I could say, what's the amount that it would take to start to precipitate? Well, what the answer would be then is greater than this, right? Greater than this value. Anything more than this starts to precipitate. Okay, if you can even just have that register with you. Okay, so the numbers that I get out of a KSP, that's the maximum amount. Anything more will cause it to precipitate. Anything less will stay dissolved. So we'll continue to practice this. Believe me, we will not go nearly as in depth with KSP though as like KA and KB. Like we're done. All we're doing now is practicing things like this. Like we're not gonna, okay, now we're gonna add this and that. We're gonna turn it all around. Just we're gonna be plugging them into KSP. Our job will be to recognize when we use the equations, when we have to use an icebox, and the packet actually does quite a good job with that. So if you didn't start it, I had asked you to start at least exercises 1 through 3. Hopefully you have. Okay.